In this video I provide a calculus-based derivation of a demand curve, about the simplest way to derive a demand curve from a utility function. So let's go ahead and look at the example. The specific example I want to use is the utility function x times y. So the way you get utilities out of this, suppose I've got 100x and 5y. I multiply the two together and that tells me that I have a utility from that bundle of 500. Just multiply the two together. So the way we can go ahead and look at this is that we're just going to go ahead and maximize utility subject to the constraint that we spend all of our incomes. This is what an optimum looks like. Now remember when we talked about the marginal rate of substitution and the price ratio, we pointed out that at this optimum, one thing that's true is that the price of x over the price of y, that's just the negative of the slope of the budget constraint. But that's equal to the marginal rate of substitution, which, if we go ahead and use calculus, the marginal rate of substitution is the derivative of x, of the utility function with respect to x, over the derivative of the utility function with respect to y. And so this is one of the equations that has to hold in the optimum of the consumer. And so that's something that we'll go ahead and exploit. Another one of the equations that has to hold in the optimum is this equation right here, our budget constraint, which sits right over here. And so we have two equations, and we're able to go ahead and use those two equations to uniquely identify this optimal bundle. First of all, I noted that the bundle, at least the way I've drawn this graph, the good that we are interested in is good x. I indicated that by indicating that good y is the composite good, or all other goods. And notice that good y has a price of 1. And so from here on, the simplification is that, well, the price of x is just the price that we're interested in. The price of y, well, that's just going to be 1. And so we have a simplification that pops out right there. And so we're going to be looking at this condition. It's a simpler case than the one that we've dealt with in the past, but it's just a nice special case so we can see where demand curves come from. So let's go ahead and take these derivatives. So let's take the derivative of the utility function with respect to x. This is the partial derivative with respect to x. We take that derivative, only y we just treat as a constant, and so we get the partial derivative of the utility function with respect to x. That's just y. Similarly, if we take the partial derivative of this utility function with respect to y, we get x. And so we could go ahead and plug into this expression and get something that will pop right out. So our slopes equal condition here, that's what this is, tells us that y, that's the marginal utility of x, over x, that's the marginal utility of y, equals the price of x. And so we could go ahead and solve this out. Price times x equals y, just multiplying the top and bottom of both sides here, or just multiplying both sides by x. So we've got this equation here, and we could go ahead and plug this in right here. So let's go ahead and do that. We plug that in, plug in for y up there, plug this into our budget constraint. We've got px plus y, but y equals another px, and that equals our income. That means that 2px equals our income. And moreover, x star, once we solve, equals our income divided by 2p. And so what we have here is a demand curve. If I give you an income, this tells you the relationship between the quantity of x demanded and its price. And another good thing about this, the higher the price, the smaller the quantity demanded. Moreover, if we were to go ahead and draw this demand curve, go ahead and erase the partial derivatives for this. Let's go ahead and draw this demand curve. We could go ahead and draw this demand curve. There's the price on the vertical axis, x on the horizontal, the quantity is on the horizontal axis. And our demand curve will look something like that. Depending on what our income is, we'll have a different one. But as the price increases, the quantity of x approaches 0. As the price decreases, the quantity of x increases quite a bit. And so we can see that this traces out a nice negative relationship between the price and the quantity of good x. And it does so in a nice general way. Notice that the way we found this is we used our slopes equal condition. Marginal rate of substitution equals the ratio of the prices. And we evaluated on the budget constraint. Those are the two conditions that define the consumer optimum, and that's all you need to know to get a general expression for a demand curve, at least in the simple case.